Hello, my name is Jesse Chotiner, and I will be doing the video for Fundamentals of Aerodynamics Spring 2026 Project 2 assignment, where we will be doing a simple Fluent 2D simulation of airflow over a flat plate. I'm doing this project with Connor Freed. I will be doing the first part of Part A, where it is showing the simulation of the flat plate from scratch and getting the contours and plots required for the project. So the first thing we're going to do is we're going to open up a new fluid flow fluent, and for our geometry I'm going to go into Inventor and do it. It's pretty simple geometry, but I enjoy doing it in the different CAD. So we're going to do a simple sketch. We're going to start our rectangle from here, and before we do that we're going to switch our units to centimeters. We're going to click apply, and we're going to go to our sketch here, and we're going to do a 100 centimeter by 50 centimeter rectangle. Our length of our plate is 100 centimeters, which is the first value, and the second value is just for some coverage. And we're going to click finish. We're going to patch that. We're going to click this, apply, and that is what we need to do. And we're going to save it in our aerodynamics folder. We're going to name it flat plate. And then I'm going to export it as a step file. Cool. And then we can exit out of Inventor. We can go into our workbench, into geometry, click import geometry, and there's our flat plate. Click open, and we're good. Next thing we're going to do is we're going to open the mesh, and we're going to create it. Alright, so the meshing tab is open and loaded, and we have our flat plate right here. First thing we're going to do is we're going to do a simple face meshing to the main face. We're going to click apply, and we're just going to generate something. And we can see these are very big squares from the default element size. But now we're going to do some stuff to the edges. And what we're going to do is we're going to go to sizing, and we're going to click the bottom edge and the top edge first. And we're going to do number of divisions. We're going to do 50 for this one, and that looks good. And we're going to click generate. And what that has done is it's created 50 different element sizes across the path and on each top and bottom, and it's making the extension from top to bottom as well. Alright, we're going to do the same exact thing, but we're going to do it for each edge. So we're going to do the inlet edge, apply, and we're going to switch number of divisions. We're going to do 60 for this one, and we're going to add a bias, which basically gives it a pattern of growth from top to bottom. We're going to do a bias factor of 70, which is basically how much is it going to grow, or how small is it going to be to get to that default value of whatever this is. And we're going to click generate, and as you can see, it has done that, and it looks weird because it starts from here. It's not on this side yet, but all we have to do to fix that is go back to sizing and click this edge, click apply, and we're going to do the same exact thing that we just did with the same amount of divisions and the same bias. Excuse me, 70. And as you can see, it's reversed. There's two ways you can fix this. You can go here and click up. You have to click it first, click apply, and we're going to click generate. And as you can see, it looks good, but what we don't want are these cells converging inwards, or I guess downwards towards the corner. So we're going to go back to this edge, and we're going to do blend the neighbors no, which means that it will stay straight on and not create that weird formation. And if we go to mesh, we have our mesh cells that get increasingly bigger as it goes up, which is good because this is where most of the analysis is going to be, is down here, and that's where we want most of the computing power. Now we're going to do some name selections. We're going to select this face first, and we're going to create air flow, and then we're going to do our inlet and our outlets. And then we're going to create we're going to do our flat plate first, actually. So we need a plate. And then we're going to name this far field pressure, which is basically just our super far out of the way from the simulation boundary, and that just is to enclose it. And as you can see, it looks good. We're going to generate that, and we're going to exit out and update that in our workbench. Alright, so we're back in workbench. We're going to click update, and we're going to give that 1 second to load. Alright, so that is loaded, and we're now going to go into the setup and actually run our simulation. 4 solver processes and double precision. That is the maximum we can use on the student license. So we're going to let this load really quickly. Alright, so it is opened, and as you can see, our mesh has loaded, and our inlet is here, and our outlet is here. So the project tells us to do this in viscous laminar, which means we just have to go to model here, and we have to go to here, and we just have to click laminar model for the viscous model. Everything else here is okay. We're going to go to materials, fluid, and solid. We're going to go to air. So next I was going to put the values in for density and stuff, and I ran into this issue before. It's reading the far field boundary condition. If we go to boundary conditions, inlet is okay as, we need to go here. It's treating it as a pressure far field, which is technically what it is, but through ANSYS it requires me to either do something with this or switch the fluid to ideal gas law, which we're not going to do because we have been given a specific density for it. But I learned that you can just move this to symmetry, click apply, and the issue goes away. If we go back to general and we check, it clicks done, and that should be good to go. That's what fixed it now. So we're going to go to air, we're going to go to density, we're going to click constant, 1.2. Viscosity is 1.8 E negative 5. Very nice. We're going to change and create. Aluminum is okay. Cell conditions look okay. Back to boundary conditions. We're going to go to inlet. Inlet is a velocity type. Very nice. We're going to it. Input that velocity, which is a free stream of 2 meters per second. We're going to go to interior airflow. Nothing there. We're going to go to outlet. This should be pressure outlet. It is. Nothing there. And the plate should be stationary. There should be no slip. Very nice. So that looks all good to go. Something I'm going to set up really quick is I'm going to go to reference values. And this is not what I wanted to do. We want to go to report definitions. And we're going to click new. We're going to click force report and drag. And the project tells us to get drag coefficient. So we're going to get drag coefficient from fluid, and then we will compare to the theoretical ones. Connor will be doing the other video of the calculations and importing the stuff. But I will be showing the contours and the plots of what we need to get. So we have the drag coefficient here, and we need to click over the plates. The only thing we can do, click OK, click close. Perfect. We're going to start our, first we're going to go to residual. We want to make these much bigger. So we're going to do 1E negative 6 for every single one. And then we're going to get ready to test. So we're going to initialize this really quick. Should take about a second or so. Alright, the initialization is done, which means we can run our calculation. We're going to put it at like 500. It should hopefully converge before that. We're going to give this a second to load. I didn't click calculate. Alright, so we're back. Number of iterations 500. We're going to click calculate, and we're going to let that run, and I will show the calculation, so I'll stay unpaused. I don't think, is it going? Alright, there we go. My apologies. Alright, so the plot has started. This is the drag coefficient, and it's already done. I shouldn't have clicked. Take 1 second to process everything. Alright, so the calculation is complete. We look at our residuals. Everything converged to the values we wanted. Calculation complete. Drag coefficient reported. So it gave us the graph, which is fine. So we're just going to go to drag coefficient and we're just going to do compute. 0.01538, very small, which means it's very streamlined, which makes sense because it's just a square. So that's good. And now we're going to look at the contours. I like to do the contours in the solver. We need to look at the velocity and pressure contours. So we're going to do that. We're first going to look at velocity, magnitude, plate. Save and display. I shouldn't have picked just that. Actually, I should pick everything. Save and display. Why is it looking like that? Give me 1 second. So the reason it looks like this actually is because I didn't switch the method, and I apologize for that. When we go back to methods, coupled, we should have used simple instead. So I'm going to rerun them really quick at that one, but that's why it just looks like the regular mesh. The value is still correct. The velocity boundary layer will increase down here as it goes along, but we want to make this look a little nicer. So I'm going to reinitialize it, and I'm going to run them, and I will show that in a second. Alright, so our new simulation is running and up and going, and as we can see, the calculation was complete. Alright, so here's the new contour that we have here. It actually, I think, was the same, but I didn't realize it. But as you can see, the whole thing is red. But if we zoom in here, we have our boundary layer that forms. And if we go to our pressures, we will see similar things. Dynamic pressure, it's the same idea. Boundary layer forming. Stagnation pressure, which in this case is mostly dynamic pressure, it's the same thing. And if we go to static pressure, this is what we are given, because it's from the frontier where there's somewhat stagnation where the velocity hits. But that's how it looks for the contours, and again, the drag coefficient is the same, but we will report it again just for good measure. Yep, 0.0158, perfect. And those are the contours, and now we're going to go into the post-CFD, and we're going to do the velocity profiles and the wall shear stress and skin friction coefficient graphs. All right, we're going to go to our excuse me, our post-CFD. We're going to go to results. Give me 1 second. All right, so we're actually back in the solver because the data didn't fully save for some reason. However, I realized that the contours you wanted to see were the vectors. So we showed the ones of the flat before, and now we're going to show the vectors. Here's the velocity vector contour. As you can see, boundary layer is forming at the bottom, and it's getting bigger and bigger and bigger. Very slightly, but it is definitely noticeable for that. And if we look at pressure, static pressure we know is the same over here. Total pressure, same as dynamic pressure. Dynamic pressure is the same as velocity. I mean, it's a little different, but that's how it looks. Now we're going to go save this and go into the post-CFD solver. All right, as you can see, we are back in Workbench, and we are going to go to results, and we're going to click edit, and that's going to open the post-CFD solver. And now what we want to do is we're gonna show the contours again, just because, but we're going to show the wall shear stress plot and the skin friction coefficient plot as well. So first thing we're going to do is we're just going to go to contour and do velocity, contour. open that, we're going to do location symmetry 1. We're going to do pressure and switch that to velocity. We're going to do like 110. We're going to click apply. And as you can see, this is our very flat and nice contour. This isn't in vector form, but it's the same idea. Anyway, what we came here to do is look at those plots and the velocity profile plots. Very important. So we're going to click on chart, and we're going to do velocity. We're going to do 25 centimeters, 50 centimeters, and 75 centimeters. 25 centimeters. And we're going to hold on. Alright, I accidentally clicked click table. So I'm going to delete this. And we're going to go to chart. So velocity, 25 centimeters. So we're going to go here. And as you can see, velocity x equals 25 centimeters. And we're going to go to x-axis, or data series. So we're going to go x-axis. We're going to click velocity as our variable. Actually, we're going to click velocity in U. And in Y, we're going to select Y. Click apply. Oh, that makes sense. Alright, I realized I forgot to insert a line at these locations. So we're going to go to insert line. We're going to do 25. I can't put a number. So we're going to go to line 1. And we're going to do this at, this is X, this is Y. We're going to do it at point, not this point. Okay, so we need to do a point at the 25 mark, the 50 mark, and the 75 mark. So our point 1 is going to be at 0. Well, we started at 0. So, and this will go to 1. So we're going to do it at 0.250, and then we're going to do it at 1. So it's going to go, or 0.25 and then 1. So it starts, or 0.5, that's how tall it is. So it's going to go from here up to there. We're going to click apply. And as we can see, that will create it. Alright, we're going to click 100 as well, just in case. So now that's applied, that's good to go. We're going to go back to insert, location, line. We're going to do line 2. And this will be at 0.5 or 50 centimeters. And that will go all the way. 100, click apply. Excuse me. We're going to go line 3. And we're going to do 0.75 for 75 meters. And click apply. Splendid. So now we're going to go to that table that we made. So I think the table just deleted itself. So we're going to create, or the chart. So we're going to create it again. We're going to do velocity, x equals 25 centimeters. And we're going to go to data series. We're going to select line 1. X-axis is velocity u. This is the y. This is the y. And we're going to click apply. And as you can see, we have our little velocity. And it's because it's very big and it goes all the way up. But it is the idea of the boundary layer being formed. If we were to go into our line 1 and be like, hey, let's just do 0.1, click apply, it gets much nicer. So we're going to keep it like this instead because it looks better. And I have to take screenshots of all these as well. So we have velocity x is 25. We're going to duplicate that, and we're going to do 50. I'm going to go here, data series, line 2. Boom. These are very too big, so we're just going to apply these for both of them. But as you can see, here is 50 as well. It looks very nice. It looks very solid. And then we're going to duplicate again, and we're going to do 75. I should have named that. Whatever. Click on line 3, and there you go. And you can see that the velocity here is increasing just a tiny bit as it goes up a little bit, as it goes further along the flat plate, which makes sense in the theory. Also, I realized these velocity graphs should actually be combined. So we're going to go here and we're going to click a new one for line 2. I'm going to click a new one for line 3 and apply. And as you can see, we are going up in that. So that's actually what we need for the data. Alright, so now we're going to do the wall shear, and first what we need to do is insert a line. We're going to call it wall shear line. And this line is going to stay 0, 0 along the Y, but it's going to just go across. So 0 to 1 is exactly what we want. We're going to do 1,000 samples for this one as well. So there's our wall shear line. We're going to go back to chart, wall shear chart. And we're going to name it that, wall shear stress. And we're going to click on, this is going to stay in the X direction, and this is going to go in wall shear. And if we click apply, that is because it is not the line that is selected. Boom. And as you can see, it's a very smooth trend. The wall shear is very big early on because that boundary layer is just forming, but as it continues to spread, it falls off a bit. And that's very good. And now we need to do the skin friction, and I believe it is not, you cannot do it in fluid CFD post without doing a variable insertion. So we're going to go back into the solver and show it there. Alright, so we're back in the solver, and what we need to do to find the skin friction is we're going to go to XY plot. We're going to go to wall fluxes, and really quick, we're actually just going to show the wall shear truss first. Alright, so if we click on the plate, as you can see, it's very similar to what we just saw in post CFD. And if we go to skin friction coefficient, it is very similar because when you find out the equation for them, you realize they are connected in similar ways, and that is about it. So yeah, so I went through the velocity contours and pressure contours with and without vectors, the plots of the 25, 50, 75 centimeters on the same graph, and the plots of the wall shear thickness and skin friction coefficient and the drag coefficient. So that's how you get them all through Fluent. Connor will do the second part, and he will show you how to export all that from Excel and analyze them so we can understand the differences between that and the theoretical. Thank you very much. Have a wonderful day.